or the problem that we did on Wednesday of week 8. And the problem was that we were pushing a loop of wire into a region of magnetic field. And for the purposes of this problem, let's say that the magnetic field is coming out of the board. And we're going to push the loop into this region of magnetic field, where the region is finite. And we're going to push the loop at constant speed, v, into the region of field. And what we're given is that the magnetic field strength is B, and the width of the wire is W, and the length of the wire is L, and the resistance in the wire is R. And so, the idea here is that we would have thought maybe before this class that to push something at constant speed requires no force whatsoever, and therefore no work. But if we're going to find the rate of work, what we're really asking for here is the power required to do this. And indeed, it does require power because there is an induced current in the loop, and that induced current, of course, dissipates power. Furthermore, the force we have to apply is the force that the magnetic field is exerting on that induced current. So here's the idea. The idea is that the work that we have to do, the work is the force over some distance. So we'll write that down. So d dt of the work is the force we have to apply over some distance. We'll call that y. So one of the things you want to notice then is that the force of a current carrying wire is IS cross B. And so the current that's in this wire is actually induced. And so the current that's induced is the EMF divided by R, so V equals IR, which is 1 over R times dB dt. Okay, so that means that the induced EMF is due to that changing flux. And so the flux is, say, B times the amount of wire that's located within the field. So we could call this some distance here, say, let's call it h. But when we take 1 over r d dt of b times h, the only thing here that's actually changing is h. And so this is b over r dh dt, and dh dt was given to us as the speed v. So we can rewrite this as b v over r. Okay, so we'll go back up here and say that the force on the wire, well, we actually need to write the sum of the forces, and so let's see, let me think about that. So the sum, so on the sides of the wire, well, which way does the current go? That's important. Okay, so the current direction means that since I'm increasing the flux, I am increasing the flux out of the page. And how I'm doing that? I'm doing that by increasing the area through which the B field points. So what my induced current is going to do, will send flux into the page. And so by the right-hand rule, in order to get flux into the page, my fingers curl into the page here when my thumb is pointing this way. And so the current goes clockwise in order to get flux to go into the page inside the loop. Okay, so that means that on the first side wire, I put my fingers in the direction of the current, so my fingers go up this way. And then I curl them out of the board. So why out of the board? Because it's a force on the induced current due to the external field, not this field up here. So that's kind of important to realize. So I put my fingers in the direction of the induced current, and I curl my fingers in the direction of the external field, and then I curl them around and my thumb points out this way. Pop. So I have a force on the wire that goes this way. Likewise, in the current that's going in the other direction, I have a force that goes this way. So those forces cancel. But the one at the top, if I put my fingers in the direction of that current and again curl them out of the board, now I get a force that goes this way. In fact, this is the force that I'm having to counteract in order to make it move at constant speed. So this force through the top, and of course there's no force in the current through the bottom. Why? There's no B field. So the only force on this thing then is going to be the force is that current, and the current is BV over R. So that's the current times the length of the wire, and S in this case is just the width of the wire this way. And I don't have to worry about the sides because they cancel out. That times the B field is the force that's exerted on the wire, and therefore the force that I have to exert to make it do that. Okay. So I have the force. Now I have to remember what I was looking for. Oh, that's right. I was looking for the power, the rate at which I have to do work, which is d dt f times y. Again, the force doesn't really change, so this is just the force, dy dt, which is the force times v, the rate at which the loop is going into the section of the magnetic field. So all I have to do is then just take my force, which is 2 factors of B times a V times a W all over R, times 1 more V, and I get B squared V squared W all over R. And that's the answer. And the other thing that you should check is to make sure that this power that I supply equals to the power dissipated by the wire. So let's just check that. The power dissipated by the wire is going to be I squared R, and so I'm going to take I squared, that's BV over R, squared times R. I have a problem. Let me think about that for a minute. Okay, I'm back. I thought about it, and I went back and I realized that these two things can't be the same, so I'm going to go back and I'm going to find my error. And here's my error. When I was looking at the flux, I didn't write down the flux, did I? I just wrote B times H, but the area here is going to be H times W, so I forgot a W. So it's H times W. And the W doesn't change, but the H does. And so there's actually a W in here. And so that means there's a, let's see, W in there. So that's the current. So there's a W in here, which means there's a W, 2 W's in here. Okay. So there's 2 W's here. So I forgot then, so I'll put then the W back in here. And now, oh, thank goodness. Now when I compare, yes, the same.